Welcome for the topical plenary session on compressible flow. Our first speaker is from National University of Defense Technology, Dr. Chaoyang Liu. His topic is thermochemical non-equilibrium effect of the hypersonic flow passing through the cylinders. Dr. Liu, please.
Sorry. Good morning, everyone. I'm Chaoyang Liu from National University of Defense Technology, and I will share with you the latest work recently. And the topic today is thermochemical non-equivalent effect of hypersonic flow passing through the cylinder. The report is divided into 4 parts. Now, first, I will introduce the background of the research, including its significance and motivation. Hypersonic aircraft can achieve a 2-hour global arrival and have broadened applications prospects in the field of space transportation. And the most respective one, including return capsule, gliding vehicles, and cruising vehicles, and so on. So, driven by flight missions, the flight trajectory of hypersonic vehicles have different characteristics. And for example, the return capsule and hypersonic glider both enter the velocity of space from outer space with a maximum flight Mach number between 10 to 20. Although cruising vehicles are always within the atmosphere, and the operating range can reach 5 to 10 Mach number or even higher. When the Mach number of the incoming flow exceeds 8, the hypersonic flow characteristics is affected by a high temperature effect. Detached shock wave is formed at the leading edge of the body, and the air behind the wave may dissociate, accompanied by complex thermal and chemical non-equivalent effects. In addition, there is interactions between shock wave, entropy layer, and the boundary layer, and speed slip may occur in the velocity field of low density region. Focusing on the hypersonic vehicles, it is of great significance to reveal the high temperature gas effect in the cylinder-induced flow fields. Oxygen and nitrogen undergo dissociations as Mach number increases, and molecular vibrations exhibit relaxation. Due to the limitations in the experimental level and the cost, it is necessary to conduct in-depth research on hypersonic non-equivalent using CFD method. Considering on the cost of flight and ground experiment, the limited information can be obtained. With the development of computer, it is feasible to use the numerical simulation to study the mechanism of hypersonic flows. We know that CFD is generally adopted for the lower altitude range, and where Nuss number is lower 1.05, in which case NS equations is applied to hypersonic flows in the continuum region. And the form of control equations can be written in the following forms, and including mass fraction, momentum equation, and the energy equation. We know that the first notable feature for the hypersonic flows is the presence of chemical non-equilibrium. Thermodynamic in chemical non-equilibrium depend on the mixing level, and the mass fraction of components needs to be solved separately. To this end, so we must namely to simulate the generation and consumption of the products, it is necessary to simulate the multi-component equations. The source term for the equation is usually solved by using the Arrhenius form, and the diffusion form is modeled using Fick's law. Another feature is the presence of thermal non-equilibrium. Thermal non-equilibrium energy undergoing relaxation process requires another temperature to characterize the vibration energy at higher energy levels. To this end, we adopt Park's two-temperature model, and the total energy is divided into two parts: translation energy and vibration energy, which can be solved through the Boltzmann distribution. And for the additional vibration energy equation, it can be written in the conservation form, with the two terms on the right side of the equation representing vibration translation energy transfer and the chemical vibration energy transfer. So we can consider another effect due to the coupling between the molecular vibration and the dissociation. It is necessary to model the coupling relationship between the two. And the QVC and the QCV can be written in the following form, where the tau represent the vibration, the relaxation time. The chemical reaction source term can also take into account the vibration effect, as shown in the formula omega S. Park proposed a professional dissociation model in which only vibration energy of high energy level can induce dissociation reactions. The coefficients are provided in the table. Next, we will conduct testing on three typical cases using HY2 based on the open form platform. The first case is a zero-dimensional analysis to reproduce the work of Cassius' PhD paper, validating our case configuration is reasonable. The single-space non-reactive heat bus model consists of a single cubic bit. Both CFD and DSMC are set with a time step of 10 to minus 9 per meters seconds, and the initial pressure is 1 atm. From the left finger, the translation temperature is set to 10,000 Kelvin, and the vibration temperature is set to 1,000 Kelvin. After a period of relaxation time, and the flow will reach equilibrium, which is in good agreement with DSMC data. For higher initial translational temperature at 30,000 Kelvin, the electrician energy effect begins to become prominent. If the effects are ignored, the predicted equilibrium temperature will be lower than the DSMC data. Considering the chemical reaction situations, the study investigated the relaxation of chemical reaction mixtures, focusing on the molecular dissociation reaction of nitrogen. The rate coefficients are present in the table, and including Park and QK models. For the non-equivalent initial working condition on the left, the Park model accurately predicts the translation temperature, but thoroughly overestimate the vibration temperature. In contrast, the CVD model predicts lower temperatures. For the initial equivalent conditions on the right side, the simulation results show a similar trend. Based on the above test, we have demonstrated the applications of solver and case configuration are reasonable. On this basis, we conduct analysis of the hypersonic flow cases, and the experiment was conducted in HEG tunnel, as shown in the diagram. For the incoming flow parameters are shown in this table, and the cylinder is installed in the middle of the test section. We use the HY2 form, and the case for configuration is provided. And the left chart represents the position of the shock wave, and the red side shows the density counter ice lines. The numerical simulation results are in good agreement with the experimental data. Using the CFD method, the predict location of the detached shock is slightly delayed compared to the experimental data. We extracted the wall pressure and the wall heat flux, and it is found that wall pressure along the flow direction agrees well with experiment data and is less by grid resolution. And the wall heat flux error doesn't exceed 10%. However, higher grid resolution is needed in this condition. Now, we compared the results obtained by considering thermal non-equivalent and thermochemical non-equivalent effects, including Mach number, pressure, temperature, oxygen distribution. The TNE case is on the upper half, and the TCNE case is on the below half. It is found that the endothermic reactions consume a significant amount of energy. So it results in that the decrease in post-shock temperature and a reduction in the standoff distance of the shock. Now we also extract the flow parameters profiles along the stagnation line with different non-equivalent models. From the above three figures, it is found that the dissolution leads to a 4,000 Kelvin decrease in equivalent temperature. And oxygen completely dissociates, and 7.78% of nitrogen undergoes dissociation. Neglecting the effect of the dissociation reaction, it results in a lower post-wave density, over estimating the standoff density by 41.5%. Now we pay more attention to the stable position of detached shock waves in the flow fields around the cylinder, which is mainly affected by the incoming flow parameters and the diameters. For the fixed inflow conditions, we now focused on the reticulars. So we have designed several operating conditions, and their geometry relationships are given in the above formula. And on the left is the geometry configuration, and on the left is the corresponding results. We have proved that the radius is positively correlated with the standoff distance, and it also affects the shock intensity and the translation and temperature. Bailey's model assumed that the gas is perfect and emitted, and Women's model, one's model is suitable for the emitted and reacting flow. Based on the numerical simulations results, we have revised the model to consider the influence of thermochemical non-equilibrium effects. For this table, it can be seen that the error is acceptable. Another case is the double cone. The physical image and the geometry scale are shown in the image on the left side. We designed control conditions, namely considering low and high enthalpy, thermodynamic non-equivalent, and thermochemical non-equivalent, and as well as temperature jump. The flow, the parameters of free stream conditions is shown in the table, with the Mach number is 10.9 and 12.82. And the reaction flow exhibits significant thermochemical non-equilibrium effects, and the right figure shows the calculation setup and the mesh distribution. the left finger gives the surface load distributions and in correlation with the experimental data and numerical results. The red side displays the vibration temperature and the oxygen distributions for different cases. The high temperature effect is significant, and the flow field structure obtained without considering dissolution is more complex, and the peak heat flux is overestimated. Now, we provide details of the flow structures introduced by double cone in the hypersonic flow, including shock waves, slip lines, and flow separation. Including complex the shock interaction and the shock separating flow interactions. Next, we'll focus on the impact of wall temperature. The left finger shows the friction resistance corresponding to different temperatures. Separation bubbles grow linearly with wall temperature, showing in the right finger, and after the fitting formula can be expressed in this form. Now, we will also compare the local flow structures and different wall temperature conditions. High temperature can induce the generation of large separation bubbles, and the separation region and shock interaction exhibit a coupled interaction. The double cone flow and the fall occurs near a critical state of shock boundary layer interactions and shock interactions. Next, we also discuss the influence of chilling edge of the double cone. With a smaller internal angle, there is no separation region presented, and only shock interaction occurs. Expansion will reflect off the wall and becoming a local high pressure region. At the chilling edge increases significantly. The expansion of a separation bubble pushes the separation shock further forward and leading to a type 4 shock interaction. And the transmitted shock compresses boundary layer significantly, resulting in several aerodynamic heating issues. At last, we'll summarize our work. Based on the HY2 form on the OpenFOAM platform, we first reduced the heat bar case in developers' PhD paper to demonstrate the reliability of the case configuration. Then we simulated the problem of hypersonic cylinder flow and improved the stagnation distance prediction model. And finally, a double cone case was simulated to analyze the effect of the wall temperature and the chilling edge angle. At the end of the report, the main reference were listed here. Thanks for your attention.
Thank you, Dr. Liu. Any questions? Over here, please.
Okay, thank you, Prof. Liu, for the nice talk. And I have one question. Maybe I missed some key points. So, how to evaluate the thermochemical non-equilibrium effect in the gas governing equations? Yeah.
You know that some non-equivalent thermal non-equivalent is always exist, but always exist in the hypersonic flows, especially for the near wall region. So we adopted the PAX2 temperature model. And the total energy is divided into two parts, namely vibration energy and translation energy. And the boundary the boundary conditions is come from the experiment.
Okay, so you mean that you evaluated this effect through the source term on the temperature gas governing equations.
Yes, yeah.
Okay, thank you. Thank you very much.
Oh.
Any other questions? Well, I have a naive one. For this kind of flow, is thermal radiation heat loss important or not? For this high temperature, is the radiation heat loss important for the dynamics of the shock?
So I didn't consider this effect, radiation effect. I didn't consider this effect. No. Only consider the dissociation of air and the non-equivalent of transportation temperature and the vibration temperature is not equivalent.
Okay, thank you.
Thank you.
Maybe last question over there.
Thank you for presentation. I have a small question about the unstudied process of the heat-based model. I saw you used the Park TTV model and the CVC model, and I saw the result of the unstudied process is significantly different. However, the results of the study results in the end is almost the same. I don't know what's the difference between these two models.
We test in the zero-dimensional analysis. The two model behave different characteristics, especially for the equilibrium temperature. However, in the two-dimensional simulations, I only used the PAX model and didn't adopt the CVDV model. Yeah.
Okay, thank you.
All right, let's thank our speaker again. Let's transition to the next talk.